It's my honor and pleasure to introduce Paul Sonier, the Chief Technology Officer of Dragonchain.
Hello. Thank you. Hello. Thank you for all coming today, and I'm here to talk about the way Dragonchain is asking us all to reimagine consensus with DragonNet. I'll preface this by mentioning I'm not a natural speaker, so I will apologize. My presentation skills are somewhat lacking at some point. Bear with me. The ideas, I think, are worth the sacrifice of listening to me talk for some period of time. All right, so a little bit on me, really little bit on me. So before joining Dragonchain, I have spent 20 years designing and developing software for various companies, various different places, Amazon, Microsoft, Disney, you name it. I've got a bachelor's degree from Carnegie Mellon University. My degree is actually in cognitive science, so I have a background with some interesting things. I've seen stuff. I've seen stuff. That's helped inform a lot of the decisions that I've made at Dragonchain and helped inform a lot of the designs that we've been coming up with. Okay. So, what is DragonNet? DragonNet is built on the Dragonchain platform. DragonNet achieves scaled consensus. So Joe gave a little talk about this earlier today in his main room presentation. And what do we mean when we say scaled consensus? So scaled consensus, if you look at the public blockchains that are out there, I use Ethereum as a common example because everyone is familiar with Ethereum, and Ethereum is what everyone's familiar with. So Ethereum achieves consensus, but it does not achieve scaling. Everyone's favorite example, mine too, CryptoKitties. So CryptoKitties sort of showed that the Ethereum network does not really scale terribly well. We achieve this by having the independent network verification nodes. So the business nodes that we call the L1 nodes are private. It's worth noting here that Dragonchain is a hybrid blockchain by definition and a private blockchain by default. So on Dragonchain, you will run a L1 node. That L1 node generates its own blockchain, and the data that L1 node takes in is kept private. We're not sharing this to the public. You're not sharing it by default to any other nodes that are out there. There is a reason for this. So what happens and how do we get the validity of the data going on? So we're using independent network verification nodes, that third bullet point there. So we are able to say, all right, external parties other than yourself can run a network verification node, and that network verification node can verify the network activity, so an incoming transaction to your level 1 node, and keep track of it. Basically take the hash of that and provide securing. Add that to its own blockchain, effectively. We'll go a little more into that in a little bit. The other main functionality of DragonNet is that we're using the scarcity of time to basically make the economics of DragonNet work. We're looking at the scarcity of time as being encapsulated in the DDSS, the Dragon Days of Slumber score. And roughly, for anyone who wasn't at the talk earlier, DDSS is an accounting for if you hold X number of dragons for Y number of days, then your DDSS is X times Y. Relatively straightforward. This is an easy thing to achieve on blockchain, since dragons are ERC20 compatible tokens. So the data about when they've been transferred or not been transferred is publicly available on the Ethereum network. And so the DDSS is not only calculatable by us, but by anyone. You can look up the balance of dragons for an account, the movement of dragons, and you can calculate the DDSS. It's relatively straightforward. It is a measure of time. It's a measure of time that something has been held. We believe that this is distinct and unique in the industry. You talk about other blockchains using things like Bitcoin proof of work, Ethereum proof of work, with Ethereum theoretically proof of stake. So DDSS is effectively proof of hold or proof of time. It's a different type of proof mechanism, and we use it in a different type of way to account for the fact that it's a different type of approach. So, the architecture. Level 1 nodes. These contain the sensitive data and your business logic that will operate on that sensitive data. These level 1 nodes are the ones that take the incoming transactions, and they will basically determine if they meet the criteria for a smart contract to execute on them. They will execute the smart contract on them. The level 1 nodes contain the smart contract. The level 1 nodes are private. They are completely private. As I mentioned earlier, I can't stress it enough. Level 1 nodes are not something that involves other people having a symmetric copy of the level 1 node. A level 1 node is a distinct level 1 node. It generates its own blockchain, and that blockchain is unique to that level 1 node. I'm stressing this frequently because this is a major point of difference between Dragonchain and pretty much the rest of the blockchain industry, so I want to make sure everyone's understanding this. It's relevant. Level 2 nodes. So level 2 nodes are where our first validation occurs. Level 2 nodes basically verify the block, that it's properly constructed, that the header has all of the information for each of the transactions that have come into the level 1 nodes, and it verifies the signatures that are involved. So it's basically performing the validation that everything that came in was properly structured and was from the appropriate signatory agents. It is not doing validation of the business logic. That's very important to understand. Validation of the business logic is kept private within the level 1 nodes. Level 2 nodes are performing basic network verification. Here I am taking a record and verifying that this network operation occurred and putting that on my blockchain. Level 3 nodes. Level 3 nodes do a network diversity verification of the level 2 nodes. So I didn't build a diagram for this, but it is in our architecture document. So you have the level 1 nodes that are effectively at the bottom. The information about their transactions, the headers, bubbles up to the level 2 nodes. Then the level 2 nodes, the information from there bubbles up to the level 3 nodes. Level 3 nodes make sure that the level 2 nodes aren't being run in a fraudulent manner. So, for example, if you say that you need a certain amount of network diversity in your level 2 nodes, you want your level 1 transactions to be validated by level 2 nodes that are, say, geographically diverse, or economically diverse, or economically sum up to a certain amount of DDSS, for example. That's all entirely viable. The level 2 nodes will perform the validation on the level 1 blocks and transactions to verify that they meet the standards of what you've defined as what needs to be your standards. The level 4 nodes, these are interesting. They serve a notary function. So level 4 nodes are not anticipated to be run by pretty much everybody out there. Level 4 nodes serve much the same purpose as sending a copy of a transaction to, or a copy of the headers of a transaction to a secure place. So it's much like going to a notary public and having a notary public basically verify that you're there and you're signing what appears to be a legal document. The notary public in that case, and anybody's dealt with the notary public before, you're familiar with this. The notary public in that case, they're not there to validate that the contract is right. They're there to validate that you showed up and you actually signed the thing. And they're not even there to validate that that's your signature. They're just there to go, okay, I've seen this. That's what they do. Finally, the level 5 nodes are where we take the information that was passed up from the level 1 nodes, level 2 nodes, level 3 nodes, level 4 nodes. At the level 5 nodes, they're constructing a blockchain, and they will eventually take the hash of their blockchain and they'll put it out to public blockchain. So there's the ability to take the data that validates the data, that validates the data, that validates the data, that validates the data. I know, sorry. And put that out onto public blockchain. When you're on public blockchain, you can then get the assurance that you've got the strength of the rigidity of the immutability of public blockchain. These things can't change once you get them out there. So an example that we use frequently is you can measure exactly how many dollars in hashing power has gone on Bitcoin, for example, if that's the public blockchain you're going to, so that you can assure that it would take that many dollars to falsify the Bitcoin blockchain in case someone really wanted to. Let's hope they don't. All right, moving on. Okay, so what we have, what we have is a novel approach. Our consensus is based on the verification from the different contexts. So we have the 5 levels. Each level performs a subtly different operation. The level 1s encapsulate the business logic, and they don't really do verification other than managing that any transaction that comes in that's supposedly intended for a smart contract is conformant with that smart contract. But the level 1, that's all that it does. Level 2s do the verification of the basic information that's been sent with the level 1s, headers, signatures, etc. Level 3s perform the validation on the level 2 data that's gone in. The level 4s provide the notary functionality, and level 5s provide the public assurance. So, very worth noting, each node at each level has its own blockchain. The nodes at levels do not share blockchains. In the Dragonchain model, the blockchains are not shared. The blockchains are maintained independently for each node. So, a level 2 node, for example, may perform the verification for a level 1 transaction, and then that level 2 node may perform a verification for another level 1 transaction. So while the level 1 node is generating its own blockchain, clicking along, the level 2 node is also generating its own blockchain, but it's stitching together the network information about those multiple level 1 nodes that are going to it to get verification. So level 2 nodes are not domain specific. They're intended to be broad, and we get a certain network effect when we get there. Again, we didn't have a great diagram for this. It's really hard to generate a good diagram for this. But effectively, you have a highly interconnected graph once you get to fairly large numbers of transactions going through the system. This highly interconnected graph is exceedingly resistant to change. So if you look at a single blockchain, any single blockchain has effectively a single failure point, which is any block in the chain. You can identify if something has been falsified, but that's difficult. It's a chain. It's a link of individual elements. What Dragonchain and DragonNet puts together is more of a network. It's more of a broad approach. And I'll go into exactly why there are strong benefits here in a second. This is the way we achieve consensus. And I just covered the non-homogeneous bit. All nodes do not contain the same information. In fact, no 2 nodes should really contain the same information, although I imagine it could happen, but it shouldn't happen for a long period of time. All right. There is no mainnet. So when I first got on with Dragonchain, pretty much the only thing I saw on Telegram was when mainnet. When mainnet, when mainnet, when mainnet, when mainnet. It's safe to say I've been waiting to present this slide for a good 9 or so months because I'm really tired of people asking that. There is no mainnet. We have a different approach. We are not doing this thing of we are launching a mainnet, which is a symmetric blockchain. That's not what we do. Please stop asking. All right. Matchmaking. So, matchmaking is interesting. Matchmaking is how we're managing the economics of DragonNet. This is kind of the core of the functionality. The base idea of DragonNet as being a set of different nodes that have different functions in terms of the validation for what's going on. That's great. When we get to this is where it's useful. So for level 2 and above nodes, level 1 nodes connect to level 2 nodes, level 3 nodes, level 4 nodes, and level 5 nodes. They connect to them through a matchmaking process. We have a global matchmaker that will return a set of matches for any requested level 1 node that's looking for validations. And it's worth noting, when we talk about the data cascading up the levels from 1 to 2 to 3 to 4 to 5, the level 1 node is mediating that entire process. The level 1 node sends the information about its transactions to level 2 nodes. The level 2 nodes respond with verification and validation information to the level 1 node. The level 1 node takes that level 2 block that's been returned and sends that level 2 block to a level 3 block, or level 3 node for verification and validation. And gets back to level 3. Level 1 takes the return level 3 and sends that to a level 4. So level 1 is basically the gatekeeper in this process. It finds those higher level nodes via the matchmaking algorithm. The matchmaking algorithm, all the nodes at a given level, 2 and above, go into a matchmaking pool. Now, they have a different size. We can think of the matchmaking pool as being a completely linear pool where every, let's say, level 2 node goes into that matchmaking pool. It's given a weighted size. So we have a weighted score for each level 2 node, also each level 3 node, level 4, but 2s, 3s, and 4s, et cetera, they for criteria. So it has a weighted size, and the weighted size is directly proportional to the DDSS score of the operator of that level 2 node, and it's inversely proportional to the price that they're charging for that level 2 node. This will make sense in a second, I swear. So when we go through the matchmaking process, the middle section there, so we make random selections from among that pool. So if you have 3 level 1 blocks that need to be validated, and you're matchmaking for a level 2 node, you'll request 3 level 2 nodes. We will generate 3 random numbers, and if we look at the entire pool that we've got there as being scaled from 0 to 1, we generate 3 random numbers within that range of 0 to 1, and we identify which of the level 2 nodes meets those numbers. Right? So the distribution there across the matchmaking pool is designed to be stochastic, but the level 2 nodes take on a greater weight based upon their criteria. So they can increase the size of their presence in the matchmaking pool by increasing their DDSS. They can also increase their size by decreasing their price. If they want to charge a higher price, they will decrease their size and therefore reduce the chance that they will be selected at any given time. This is a nice, clean economic effect. It's simple, it's straightforward. Now, if it's just that, we enter into some issues. That's counting down, thank you. If it's just that, we have some problems. But the level 1 nodes, at the same time, have also got some scarcity-based or time-based process. So we see here in the matchmaking request section, we've got the level 1 nodes. The top one there, it was the same color, top of the one, I'm sorry. The top one, so the range across that, that's the time in a block. A block in Dragonchain is 5 seconds, so that's 5 seconds. A Dragonchain that's running as an L1 node that has a low DDSS, a low Dragon Days of Slumber score, will be allotted a single matchmaking request. It can make a request a single time based upon its DDSS. If it has a super, super low DDSS, the lowest DDS score possible, DDSS score possible, it will have to wait until the block is almost complete to be able to submit a matchmaking request. If it has something higher, it will wait less time. Now, if the level 1 node has a medium level DDSS, sorry. Can't read these very well from here. Then it can get multiple retries. So it not only gets to try sooner, but it gets to try repeatedly during the same block. So you can see there, it's about, trying to get that about, what is that? 30% of the way, the first one walking from the left to the right. So we'll have to wait 30% of the time of the block to do its first matchmaking request. We can then make its second matchmaking request at 60%, third matchmaking request at 90%, right? The effect of this is that L1 nodes that have a high DDSS get a high matchmaking retry count. It's worth noting that you are not guaranteed to get a compatible L2 or higher node on matchmaking. You will get a completely random selection of those nodes in the matchmaking. It may be that if you are trying to set a very low price on the transactions that you're willing to pay from the level 1 to the level 2 or level 3 or level 4, that you may only be able to get, say, 10% of the nodes that are available in the pool as scaled by the weight. So that would mean on average, you will have to make 10 requests to get the number of nodes that you need to perform your validation. Normally that would be a problem. However, that means that as your DDSS goes up, if you have a high enough DDSS, you can make the 10 requests within the same time period, within the same block. The effect of this is that at a higher DDSS for a level 1 node, you can basically pay less for your transactions. Your DDSS allows you to pay less because your retry time is higher. You're getting more frequent retries. Frequency is higher, sorry. You get more retries. So on the requester side, we have a clear economic incentive to allow you to define exactly what your cost is going to be in terms of your transaction submission, and to determine exactly how long you expect your transactions to occur based upon your cost. You have two ways to modify that. You have price, you can pay more, or you can increase your DDSS more, right? On the L2 and higher node level, at the same time, you have two primary variables. One is your price, and one is your DDSS. Those are both put together into your weighted number, and your weighted number determines your likelihood of getting selected at any given block. Again, you can increase your likelihood by decreasing your price that you're expecting to get paid, or increasing your amount of DDSS, increasing the amount of encapsulated time, DDSS, that you're going to put into it. This roughly, not even roughly really, this is the solution to the mining and transactional cost problem in Dragonchain. So level 2 through 5 nodes are basically the version of mining that exists on Dragonchain. These nodes exist to allow for network consensus to occur on Dragonchain. At the same time, the ability to set the price, have your number of retries on level 1 is very much equivalent to, for lack of a better example, the gas price on Ethereum, and the ability to alter your gas price and to choose the latency that you're willing to accept for the amount of time that's going on in your blocks. It's a little, I'm seeing some confused faces. Sorry, it's a little tricky, but it works. it works nicely. All right, scarcity. Scarcity drives economic models. We cannot stress that enough. Without scarcity, there are no economic models that are possible. I had my kids, say, I wish money grew on trees. And I had to explain to them why that's not a good idea. Because if money grew on trees, then everyone would have so much money that no one would have any money at all. Line from The Incredibles, everyone is special, then no one is special at all. You have to have scarcity. Scarcity must exist in some sense for there to be a functioning economic model. Scarcity is effectively low in the cloud. The cloud has, when we talk about running compute jobs in the cloud, if you've got something that scales horizontally and you're looking to put it up in AWS, pretty much whatever your job is, AWS will be able to handle it. Infrastructurally, there's going to be some work that's going to go on, trust me. But AWS can handle it. They've got the resources. And back in the early days of S3, I was one of the people going, well, what happens when Amazon runs out of hard disk space to put storage on? And the answer was, they'll buy more hard drives. Oh, that's right, because they're margin positive about everything they're doing, so they can scale out effectively. They're rolling in their cost of all the IT management and support that's involved there to basically be able to scale out horizontally. All clouds do this. But it does affect what we look at in terms of scarcity. So what we're using for scarcity is DDSS. You can add resources to a system and effectively decrease the scarcity, but you can't add time to a system. Time is, you can't falsify it. In particular on blockchains, Ethereum, the time of a transaction, the block height of a transaction is fundamentally locked in to that transaction. You can identify that transaction, you can see exactly how far away it was. That doesn't change. DDSS is a way of us defining exactly that scarcity of time, that scarcity of that accumulation of time that we've got in there. All right. Scaling. So theoretically, scaling can be unlimited. Again, for good horizontally scalable tasks or projects, things can scale infinitely. One of the things that's a fundamental design problem with most existing public blockchains, most, not necessarily all, is that they are designed to handle a set of loads that will scale slowly. So Ethereum will scale up the amount of effort that can be done on the Ethereum blockchain, but it scales slowly. Bitcoin scales very poorly, and only with a fair amount of engineering effort and a fair number of forks and you name it. And that's a little bit strange in the world that we live in. We live in a world where the ability to scale a task or scale a set of tasks is and should be effectively unlimited. There is not, by any definition, there was a reasonably strong limit on the number of computers that could be attached to the internet as long as IPv4 was out there. There was effectively a fork that was required when we switched over from IPv4 to IPv6, because IPv4 defined a 32-bit address space for IP addresses for machines on the internet. If you were around 10 years ago or so, there's a big thing about we're running out of IP addresses, et cetera. And yes, we were indeed running out of IPv4 addresses. Then we have IPv6 introduced. And now I think there's enough address space to give, what is it, every electron in the solar system its own IP address. There's plenty of space, basically. We're not running out anytime soon. But the point here is that the internet does not have any strict restrictions on scaling. If you want to get a new computer and stick it on the internet, great, have fun. It's good, it works. It doesn't require any unusual gymnastics. So public blockchains are not necessarily like that. If you want to add additional load to public blockchains, then it doesn't necessarily scale, even when you add more gas costs. CryptoKitties. It's gonna say CryptoKitties. Everyone's been there to CryptoKitties. I was trying to do some transactions on Ethereum when CryptoKitties was big, and I was getting very frustrated that I was paying, $30 for a transaction that would take 6 hours to go through. That sucks. That just sucks, plain and simple. We don't have that issue, Dragonchain. Orders of magnitude increase. Multiple, 3, 4, 5 orders of magnitude increase in the number of transactions that are submitted will not affect things. And the reason for this is that we are not using symmetric blockchains. We're not using blockchains that are being shared across nodes, and they require multiple nodes to synchronize with each other to make sure that they've got the same data to come to a consensus. Our consensus is network-based, and that means that we are at, effectively, internet scalability. We can achieve internet scalability very simply with our architecture. And the reduced exposure to flood attacks and similar CryptoKitties. CryptoKitties. It's just the best example everyone's seen. You get a popular dApp that's out there, and all of a sudden your transactions just are taking forever and costing you a ton of money. That doesn't happen on Dragonchain. That just does not happen on Dragonchain. There may be some point at which the number of transactions that you're submitting are large, but we scale very quickly too. The economic incentives to spin up an additional node are high, and there's other things I won't mention. It's good. Okay. I would imagine there are questions, because this is sort of a big thing. I've been thinking about this for a while, working on it, working on the design, working on the implementation. We appear to have a microphone. Anyone have any questions? Please.
You had the chart about, I took a picture of it, sorry.
Here, I'll move it back. Try to move it back.
It's the one with all the bars.
Yep.
Okay, yeah, the matchmaking process. So if you have DDS and you have a DDSS and you have a price, is there like an optimal amount or configuration or combination that might yield the most nodes? And is there a way that maybe Dragonchain supplies that, and maybe you determine,
Yeah.
gee, that's the optimal, but I want to be above or below that price or something?
No, that's a super question, actually. So we haven't predefined any optimal, and the intent is that we don't want to define any of those economic factors. When you come in and start saying, oh, here is where we want things to be economically, that's a little iffy. That's not a great solution. The approach that we're looking at is, and we haven't got this yet, but it's relatively simple lift. We're going to put together some tools that will allow you to have some predictions based upon, given your current DDSS and given the current price that you're charging, you can expect to get these many transactions coming in at your requested price over this period of time. That's basically the idea. And then the idea will be, okay, what happens if I increase my price this much? All right, then you'll see revenue go down by this much. And what happens if I increase my DDSS by this much by some means? Okay, then you'll see this. The tool that made this all really clear to me, and the same thing, by the way, applies for the level 1 nodes. So there is that trade-off between the level 1 nodes DDSS, the price they're willing to pay, and the time that it takes for a block of transactions to be fully validated. It's the Ether gas station. So ethgasstation.net, I think it is. It's the website that lets you basically look at what the current network conditions are on Ethereum and identify, all right, based on those current network conditions, if I pay 4 gig away, how long is my transaction going to take to flow through Ethereum? That's useful. That's great. I've used it before myself. It's phenomenal. It's fantastic. We'd have something both on the L1 side to say, okay, if I pay this much given my DDSS, how long is it going to take for my transaction to be fully verified up to level 5 level? And then also on a level 2 through level 5, we have the ability to generate the same tool that says, all right, similar tool. Given my DDSS and given my price, how many transactions do we expect to see coming in at that price? And so how much revenue do you expect to be making over a given period of time? So it's predictive analysis. And we're not trying to identify exactly what the right number is. You figure out what the right number is, but there's a trade-off. The way we're making it work is because it's all based on DDSS. And the Dragon Days of Slumber score determines that scarcity that keeps everyone from saying, well, I want to take all the traffic, so I'll charge the least. So I'll just charge the lowest amount possible, therefore I'll get everything. Sorry, you can do that, but it will affect your ability to get match made against. Your bar in the top there will become super small. Yes. It will become large, but it'll only become as large as your DDSS allows it to get. Right? So, and again, there's a trade-off. I don't know what the curve actually looks like. There will probably be a curve that goes, okay, for this DDSS and this price, and you change your price, you'll get this pricing curve. I don't know what that is yet. Yeah. It's, like I say, I expect it to be a tool that dynamically looks at the existing current network environment and says, based upon the current network conditions, here's what we're expecting to see. Much like the Ether gas station, they can tell you what the state of the network was as the last block that they got. Is it going to change in the next block? Probably. Do we know how it's going to change? Hell no. So we're not going to bother trying to, do a complicated modeling. We'll just let you sort of make your decision as to what's right for you at this current time, given what you're seeing. That's roughly the idea. Let's get you the microphone.
Hi. So I just want to kind of make it clear so I understand it. So you kind of solved the scaling issue by sort of giving priority depending on the amount of DDSS being used, right? So like it kind of solves the microtransaction issue by giving less retries to smaller DDSS. Is that correct?
Higher DDSS.
Higher,
yes.
okay.
More retries, higher DDSS. Basically, higher DDSS is always better. So right. The more time you've accumulated with your Dragon Days of Slumber score, the better you'll get. So you're able to do more retries as a level 1 node, and therefore reduce the overall time that it's going to take for all your transactions to go through. As well, it will reduce the effective cost that you have to pay, because if you're willing to pay a cost that only gets you, as mentioned earlier, 10% of the matchmaking pool, for example, but you can try 10 times in the same block, that means to get those transactions validated, it will take you an average of 1 block to get those transactions validated. Okay, 11%, whatever, sorry, the limit thing. But that's roughly the idea. He's coming.
This is great. So a couple of questions, and you may touch on it in different talks. But one is, of course, what is going on with DDSS as you accrue it, as you use it. You're going to use it as a utility. You're going to build things on it. You want to acquire it as a client enterprise, that kind of thing. The other side is as a owner of token and then accruing DDSS and running a node, right? So there's two different operations. When it comes to November and you're on the roadmap and talking about leasing of DDSS or pooling it, I can see where companies, clients, would want to have a high DDSS, their cost is less, they have more retry opportunities for validation, so I see that. Versus sale of or transfer of to that company through sale, I like, but I don't know a lot about what's going to happen in November with the concept of leasing. Is that something that can be pulled back, like almost like delegating in Steam, and you're delegating power, and then you can pull that back at the end of a lease, or if a different company or a different client needs that retry opportunity, then they can lease a higher, they can basically pool together a higher DDSS for them, but they're basically paying a lease cost to get it, right?
Right, right.
Is that
So,
basically the structure versus sale, that client buying more token and accruing their own DDSS and leasing it for a now opportunity to retry and utilize the network?
that's correct, yes. So we've got several things in the works, several projects in the works, and they're not all internal, to basically productize DDSS. So the ability to sell DDSS. Let's say you've held on to a large number of tokens for a long period of time, and you've accumulated a large quantity of DDSS, you're not planning on using it. That DDSS, according to this process, has economic value for both level 2 through 5 node operators and level 1 node operators. You can take that DDSS, that's an accumulation of the time accumulated on your dragons that you've held, and sell or lease that DDSS without moving the dragons at all. You can keep the dragons, but sell the value that you've accumulated for them effectively. This is why we look at it as being effectively an alternate proof mechanism. That's, I hate to draw the analogies to proof of stake, because proof of stake is a little different, a little weird on this. But roughly, the idea within proof of stake is you're saying, I want to leverage the value of my accumulated value, right, without moving that value, right? So I will stake my tokens to be able to assert that these blocks are going through. That staking pool gets some proportion of mining rewards, etc. Boom, you're good. You haven't spent your tokens, but you've staked them effectively. You've staked some value of them. We've slightly inverted the concept with DDSS. So now you have the ability to either sell or lease for a given term some quantity of DDSS that you've accumulated on your dragons, right? To then help other people accumulate to get better value off of their transactions. It's a different but similar concept. It takes a little while to get your head around, honestly. It took me a little while. But it's strong. He's going.
On the question of staking,
Yeah.
how's the staking perform? Is it you're actually pulling the tokens out of the user's wallet and then putting in escrow, or how does staking work on Dragonchain?
So, like I said, we're not doing exact staking per se. So let's say you as an individual have got some Dragon tokens. Hope you do. Good idea. You want to run a level 1 node, right? So you will associate your Ethereum address with your Dragonchain account, and the dragons that are associated with that Ethereum account are the ones that determine your DDSS. So you don't have to move them to be able to use your DDSS in that manner. If you want to sell or lease it, it's a slightly different manner. So at that point, you're not moving the dragons out of your account, because by moving the dragons, again, Dragon Days of Slumber score, they accumulate the DDSS as long as they stay in one spot. When they move, they lose that DDSS. So if you want to sell or lease that DDSS, you keep the dragons where they are, but then we have ways of basically allowing that DDSS, which is accruing on top of the dragons, to be moved without moving the dragons themselves. So that DDSS can be moved to another interested person, but you keep the dragons. Does that answer your question? Correct. The question was, if the DDSS is separated from the dragons, then would the owner continue to accrue DDSS on the dragons that remain in their account? That's entirely correct, yes. So if you sell the DDSS that's accumulated on your dragons in your account, and you keep the dragons around, obviously, then they'll keep accruing DDSS. At some point in the future, you will have as much DDSS as you sold previously, and you can sell it again. There's a value to accumulating that DDSS. It's again, we consider it to be value accumulated over time. We're placing a value on time. You can sell portions of it. Yeah. We're still working out some of the mechanics on this, honestly, but you don't need to, your DDSS doesn't need to go down to effectively 0 when you sell it, so you can sell some proportion of it. And there's some quantity, again, when we do the calculation of exactly, if you want to say, okay, if I increase my DDSS by this amount, then my transactions will take this long with this price, you can find the sweet spot for you and purchase just that exact quantity of DDSS. That's not a problem. And for what it's worth, we anticipate creating a marketplace on which, although it's maybe done by a third party at this point, on which the DDSS can be bid on and sold. So you can say, I have this much DDSS that I'm not using, and I'm willing to sell it. You basically put it out there, and someone says, hey, I'd like my transactions to be cheaper, and I'm willing to pay for that functionality. If what they're willing to pay is equal to what you're willing to sell it for, then boom, done. So there's no, you don't have to go out and find someone with dragons and beg them for their DDSS. Microphone's incoming.
What's the difference between work and trust, and especially on the different node levels?
Sorry?
The difference between work and trust?
Oh, sure. So proof of work basically indicates that this amount of work in some manner has gone on. So Bitcoin. You've proven that you can find a SHA-256 hash that's got X number of leading zeros with a nonce. Okay, that takes work. You've proven that. Trust, we trust you that you're doing it right. Trust is, you're good. Trust is effectively implicit in our level 1 nodes. Because they're level 1 nodes and they're private, it's private blockchain, then we trust that if you have access to submit a transaction to your blockchain, that you're not going to submit a fraudulent transaction to your own level 1 node. I mean, hey, if you want to, whatever. But you get my point?
Is there a difference with level 2 nodes, level 3, 4?
Yes. So at level 2 nodes, we're basically doing proof of work. It's not gigantic. We're not doing a huge amount of hashing power. And again, the reason is that the level 2 nodes they're not symmetrically replicated across a network of level 2 nodes. So the amount of work a level 2 node does is going to be just being done on that level 2 node. We can say, all right, what's the total capacity that this level 2 node can do to keep up with the number of transactions that's getting submitted, and we can do that amount of work. It's not gigantic. And the reason why this isn't a gigantically critical thing is because, as I mentioned earlier, blockchains are by definition chains. They're one thing to one thing to one thing to one thing to one thing, right? Proof of work is required to be strong in those blockchains, because if proof of work is not strong, you have the ability to effectively, fraudulently impact these, right? What we have, on the other hand, is a network. And the network is strongly resistant. So a level 2 node could theoretically be compromised. Right? I hope it doesn't, but it could theoretically be compromised. But that level 2 node is being referenced by, and that blockchain the level 2 node is generating is being referenced by every level 1 node that's ever accessed that level 2 node, and being referenced by every level 3 node that ever was provided that level 2 node's blocks for validation and verification. So that proof of work is less critically necessary to falsify a level 2 node's blockchain, or level 3, whatever other levels. Effectively falsify it, right? You would need to also falsify all of the other nodes that have ever pointed to that level 2 node, or at least since the point at which you want to falsify it, right? It's a strong network effect. If we look at it in computer science terms as a deeply interconnected graph, right? Deeply interconnected graphs are hard to falsify things on because they're deeply interconnected. There's a large quantity of interconnections that say, all right, if one of these is wrong, or if all of these are wrong, for example, pointing to a single level 2 node, then you know that a falsification happened at that level 2 node. And again, it's worth noting that any failure at that level 2 node on that chain, that level 2 node might be invalidated, but because we're not symmetric, because all the operations are going on network-wide, there are thousands of other level 2 nodes that are out there that are performing additional validations. So that level 2 node becoming falsified and invalid doesn't necessarily invalidate any of the level 1 nodes that submitted a transaction at level 2 node, because they're also submitting other level 2 nodes frequently. They're matchmaking at a frequency basis that we're defining up there, and that basically makes them promiscuous. They involve promiscuous matchmaking. They're going out and they're connecting to a bunch of different things, and that basically makes it much more secure.
Thank you, Paul. Very meaty and satisfying.
Thank you. Thank you very much.
Okay, that's, I think, DAP's room for today. Tap room talk is, where's tap room talk? In consensus, I assume I think that's what I remember too. Okay, so we'll see you all tomorrow, hopefully here or in the node room on the 3rd floor upstairs. And the